Welcome to this third video for validity and screeners. We're going to jump ship to using MTMM as a confirmatory factor analysis from a classical test theory perspective. Let's review tau equivalency. It's often referred to as parallelism. It's a specific type of measurement model that assumes that all items within a test measure the same construct, i.e. a single underlying factor, and have the same error variance. It's an idealistic model that posits a perfect relationship between the items where each item is equally difficult and discriminative. In a tau equivalent model, the observed score X can be represented as T plus E, where T is the true score, common to all items, and E is the error term, assumed to have the same variance for all items. It has importance in psychometrics because tau equivalence is the foundation to classical test theory and has implications for the interpretation and generalization of scores. It provides the basis for calculating a single reliability coefficient for the test, which can be applied universally. While tau equivalence is useful in theoretical concepts, it's rarely found in real-world data. Items within a test often vary in difficulty and discriminative power, leading to differences in error variances. This discrepancy between the theoretical model and actual data has led to the development of more flexible models like congeneric equivalence, which allows for different error variances across items. Remember that reliability refers to consistency or stability of a test. If it's reliable, it produces similar results under consistent conditions, and it's represented by the symbol R. This is a measure of consistency and range from 0, meaning no reliability, to 1, perfect reliability. We have test-retest, parallel forms reliability, internal consistency, and inter-rater reliability. Now, if the assumption of tau equivalence holds, calculating the reliability coefficient becomes a straightforward process, as all the items have the same relationship with the underlying construct and the same error variance. In the absence of tau equivalence, more complex models are needed to accurately assess reliability. While reliability is crucial, it does not ensure validity. Therefore, reliability is necessary but not sufficient for a good measurement tool. The multi-trait, multi-method matrix. Understanding the complex relationships between psychological traits and the methods used to measure them is a fundamental challenge in psychometrics. The multi-trait, multi-method matrix is an analytical framework that provides insights into these relationships by quantifying the convergent validity, discriminant validity, and reliability. Recall that convergent validity is the extent to which different methods of measuring the same trait correlate with one another. Discriminant validity is the extent to which different traits are distinct from one another, regardless of the method used to measure them. And reliability is the consistency of a measurement, indicating how well a method measured a trait without random error. An MTMM matrix is typically square, with rows and columns representing different traits and methods. It consists of three main parts: the monotrait hetero method, MTHM correlations. These are correlations between the same trait measured by different methods. We also have the heterotrait mono method, HTMM, and the heterotrait hetero method, HTHM correlations. These represent correlations between different traits, either through the same or different methods. And then we also have our reliability coefficients that are placed on the main diagonal of the matrix, representing the correlation of a trait with itself by the same method. MTHM correlation should be different from 0 and typically higher than both HTMM and HTHM correlations. A strong MTHM correlation supports the notion that different methods are tapping into the same underlying trait. Sometimes correlations between different methods measuring the same trait may be low due to specific method variance. Also, for thresholds, determining the acceptable threshold for MTHM correlations can be subjective and context specific. An example is measuring depression using self-report, clinician rating, and family member reporting. The correlations between these different methods for the same trait should be high. Assessing discriminant validity through MTMM. HTMM and HTHM correlations should be consistent across different method blocks, demonstrating that the relationships between different traits are stable across different measurement techniques. Discriminant validity is further supported if MTHM correlations are higher than HTMM and HTHM correlations. Some challenges and considerations for trait definitions. Clear and distinct definitions of traits are essential to observe discriminant validity. There's also methodological overlap because overlapping methods may lead to inflated correlations, which challenges discriminant validity. For an example, in an MTMM assessing personality traits, the correlations between extroversion and neuroticism should be lower than the correlations between different methods of measuring extroversion. Reliability coefficients. These coefficients are placed on the main diagonal, and they represent the extent to which a measurement is free from random error. Remember that while reliability is necessary for validity, it's not sufficient by itself. A scale measuring anxiety should produce similar scores under consistent conditions, reflected in a high reliability coefficient in the MTMM. MTMM has been utilized in various fields, including clinical psychology, educational assessment, and organizational behavior. However, there's always some limitations. Complexity. Interpreting MTMM can be complex due to multidimensional nature of the matrix. It also relies on assumptions like tau equivalence, which may not hold in real-world data. And there's also potential biases in individual methods that can affect the entire method. Let's look at some notations and subscripts. T is the trait. This refers to the specific characteristic or attribute being measured. In psychological studies, a trait can be something like PTSD, depression, or anxiety. An example, if you're measuring PTSD, T1 might refer to a specific symptom of PTSD, such as intrusive thoughts. If you were measuring multiple symptoms or multiple disorders, you'd have T2, T3, and so on. For M, this is the method. This refers to the method used to measure the trait. Methods can vary widely, from self-reports to clinician ratings to third-party observations. In the context of PTSD, M1 might be a self-report questionnaire about symptoms. M2 might be a clinician's rating based on an interview, and M3 might be a family member's observations. R is the correlation coefficient, which is the extent to which two variables change together, ranging from -1 to +1. HT, this is the heterotrait. This refers to different traits. For instance, if you're studying PTSD and depression simultaneously, PTSD and depression would be considered heterotraits to each other. HM, this is the hetero method. This refers to different methods used to measure a trait. If you're using both self-reports and clinician ratings to assess PTSD, those would be hetero methods. MM is the mono method. This denotes the same method that was used to measure different traits. For example, if you're using a self-report questionnaire to assess both PTSD and depression symptoms, that's a mono method. It's the same method for two different traits. Now let's break down the correlation notations. R sub T1 minus M1, T1 minus M2. This represents the correlation between the scores of a single trait, T1, meaning a specific PTSD symptom, measured using two different methods, M1 and M2. R sub T1 minus M1, comma T2 minus M2. This is the correlation between two different traits, T1 and T2, meaning a PTSD symptom and a depression symptom, measured using two different methods, M1 and M2. R sub T1 minus M1, comma T2 minus M1. This shows the correlation between two different traits, T1 and T2 again, but measured using the same method, M1. The subscripts serve as a systematic way to denote which traits and methods are being compared in a given correlation within the MTMM matrix. By understanding these notations and subscripts, you can clearly navigate and interpret the relationships and comparisons being made in the matrix. If you're measuring PTSD symptoms using three different methods like self-report, clinician-rated, family member information, the reliability coefficients for each method should ideally be close to 1. A coefficient of 0.8 or above is generally considered good, while below 0.7 might indicate that the method is inconsistent. Let's think of some sample interpretations. High reliability, 0.9. This method is highly consistent. Moderate reliability, 0.7. Some inconsistencies might exist. And then we have low reliability, 0.5. The method may be unreliable. Let's look at convergent validity correlations. That should be different from 0. Remember that convergent validity correlations should show a positive relationship, indicating that different methods measuring PTSD symptoms agree with each other. If a self-report and a clinician-rated method both measure PTSD severity, the correlation, for example, R sub T1 minus M1, comma T1 minus M2, should be significantly different from 0 and ideally close to 1. Let's think of some sample interpretations. Close to 1 means strong agreement between the methods. Moderate, meaning somewhere between 0.6 and 0.7. There's some agreement, but there's some inconsistencies. And close to 0, the methods do not agree, which could indicate a problem with one or both methods. Let's look at convergent validity correlations and how they should be higher than HT-HM correlations and HT-MM correlations. Convergent validity correlations should be higher than comparisons involving different traits. If comparing PTSD symptoms again to a different trait, like depression, the correlation between different methods for PTSD, such as R sub T1 minus M1, comma T1 minus M2, should be higher than the correlation between PTSD and depression. For example, R sub T1 minus M1, comma, T2 minus M2. Some interpretations. High convergent correlation, low heterotrait correlations indicates good construct validity. Low convergent correlation, high heterotrait correlation suggests problems with the methods or understanding of the traits. Heterotrait correlations are consistent across method blocks in an ideal situation. This means that the relationships between different traits should be similar regardless of the method used. If comparing PTSD to depression using different methods, the correlations, for example, R sub T1 minus M1, comma, T2 minus M1, or R sub T1 minus M2, comma, T2 minus M2, or R sub T1 minus M3, comma, T2 minus M3 should be similar. Some sample interpretations, consistent correlations indicate that the methods are not introducing bias. Inconsistent correlations may signal that one or more methods are biased. Rater effects refer to the biases and tendencies that raters bring into their evaluations. These biases can stem from cognitive shortcuts, personal values, cultural backgrounds, and individual differences in interpretation and perception. We have the halo effect, generalizing one positive trait to an overall positive rating. We have severity and leniency bias, which is the tendency to rate consistently high or low. We have the central tendency bias, which is avoiding extreme judgments, rating everyone near the middle of the scale. We have the contrast effect, rating someone relative to others rather than to objective standards. The impact of rater effects. Biases can lead to skewed or distorted evaluations, and different raters may produce significantly different evaluations for the same individual. To address these effects, providing raters with clear instructions and training can mitigate some biases. Techniques like MTMM, confirmatory factor analysis, can account and control rater effects. An example in assessing child behavior for ADHD. Assessing symptoms of ADHD requires evaluations from multiple sources, such as teachers, parents, and self-reports from children. These different perspectives inherently introduce bias into behavioral ratings. For teachers, they interact with many children daily and may compare children to each other. Parents may have biases due to emotional attachment or expectations, and children have limited self-reflective ability and may impact the accuracy of their self-report. Some traits to be evaluated may be the inability to sit still, short attention span, or being easily distracted. To apply this in a CFA, to utilize MTMM, a matrix can be constructed with the different methods, so teacher, parent, self-report, and the traits as described above. Ensuring that different methods converge on the same traits and are distinct from other traits helps you analyze convergent and discriminant validity. And to control for rater effects, you want to apply confirmatory factor analysis that allows for controlling biases introduced by different raters. Some techniques to control rater bias, using multiple raters to counterbalance individual biases. You can also use latent variables to capture the common variance shared among different raters, separating it from method-specific variance. You can also train raters to recognize and minimize biases using standardized instructions. Providing feedback and monitoring rater performance helps ensure consistency. Some other clinical examples and considerations, well, rater biases are not limited to ADHD assessments. They can emerge in various clinical contexts like personality assessments, where different perceptions of normality and abnormality occur. Performance evaluations, biases stemming from interpersonal relationships. Medical diagnoses, subjective symptoms are reported by patients. Some limitations and challenges. There's complexity of human judgment. Not all biases can be easily quantified or controlled. Raters may also resist the idea that their judgments are biased. And different settings and assessments may require specific techniques to manage biases. Confirmatory factor analysis applied to MTMM helps researchers define the theoretical model that posits how traits like PTSD symptoms and methods, self-report, or clinician ratings relate to underlying latent factors. It allows researchers to model method effects, thereby separating the influence of the method from the actual trait being measured. Some key components in MTMM CFA are the trait factors. These are the underlying constructs the researcher aims to measure, like symptoms of PTSD. We have the method factors. These reflect the systematic bias or variance associated with different methods of measurement. And then we have error. This represents the random variability not captured by the trait or method factors. In MTMM-CFA, the researcher specifies a model that includes both trait and method factors. The trait factors are connected to the corresponding trait indicators across different methods, while method factors are connected to different traits measured by the same method. In the CFA approach to MTMM, one must decide whether to assume that method factors are orthogonal or oblique. For orthogonal method factors, this assumption posits that the method factors are uncorrelated with each other. It implies that the biases introduced by different methods are entirely independent. For oblique method factors, this approach allows method factors to be correlated, recognizing that different methods might share some systematic biases. So, are orthogonal method factors a reasonable assumption? Well, this question about whether to assume this is complex and depends on the specific context of the research. There are some advantages of the orthogonal assumption because it gives you a simpler model, because it reduces the number of parameters to estimate. It also is a clear interpretation. By assuming no correlation between method factors, the interpretation of each factor remains straightforward, but it's unrealistic in some contexts. In some cases, different methods may indeed share biases. For instance, self-report and parent report might both be influenced by social desirability, making the assumption of orthogonality unrealistic. There's also empirical evidence. Some studies have shown that method factors are often correlated, casting doubt on the universal applicability of the orthogonal assumption. For empirical testing, it may be advisable to test both orthogonal and oblique models within a given data set to determine which provides a better fit. Let's look at an example. We all hold perceptual biases and have our own response styles. These biases and styles give rise to what we call the rater effects. These effects are largely unconscious and come into play whenever we're asked to question or evaluate objects in our social environment. They become particularly salient in various clinical settings, such as the assessment of child behavior, mental health evaluations, performance assessments, and more. Let's look at our example on ADHD. And here's our last slide. Recall our different traits: unable to sit still, short attention span, or easily distracted. We have different raters, so teachers, parents, and children. These differing perspectives introduce bias into behavioral ratings. And can we control for these biases? Yes, and that's where MTMM-CFA comes into play. So we build the model by creating a 3x3 matrix. And that's because we have 3 symptoms, the traits, and 3 methods, teacher, parent, and child self-report. The trait factors, these represent the underlying ADHD symptoms we're trying to measure. The method factors, these capture the biases specific to each rater, the teacher, the parent, or the child, and the error. This includes random variability not captured by traits or methods. Convergent validity checks how well different methods agree when measuring the same trait. In this context, it means looking at the correlations between different raters for the same ADHD symptom. High convergent validity would indicate that different raters are consistently rating the ADHD symptom similarly. Discriminant validity checks the distinctness of different traits within the same method. It ensures that different ADHD symptoms are being rated as separate constructs by the same rater. Reliability coefficients ensure that the measurements are consistent. High reliability means that if this assessment were repeated, similar results would be obtained. By explicitly modeling method factors, MTMM-CFA allows for the separation of trait variance from method variance. This separation enables us to cleanse the ratings of ADHD symptoms from the biases introduced by different raters. To have a better understanding of ADHD, by controlling for rater biases, we get a more accurate picture of a child's ADHD symptoms. This aids in better diagnosis and intervention planning. This method provides insights into how different raters perceive the same behavior, allowing for tailored communication and collaboration between teachers, parents, and clinicians. And by addressing rater biases, the assessment's overall reliability and validity are strengthened, leading to more trustworthy conclusions. Some challenges. MTMM-CFA is a sophisticated model requiring careful specification and robust statistical knowledge. The decisions about orthogonal versus oblique method factors, error structures, and more require theoretical and empirical consideration. The insights from MTMM-CFA need to be translated into practical actions, such as individualized education plans or parent-teacher collaboration strategies. This scenario of assessing ADHD symptoms through different raters provides a concrete example of how rater effects can complicate the evaluation process, which will be expanded on more in lab.